Hello, my dear child. So, today we are going to start with an extremely interesting as well as an extremely important chapter in your chemistry syllabus, which is called as the measurement of matter. And this particular chapter begins with the definition of the term matter itself. And to introduce that definition to y'all, I have made y'all come into my own personal classroom. Now understand, if we read over here, it says, when we observe the world around us, we see millions of substances. Now in this particular classroom, what are the kind of objects that you and I are able to see? Let me highlight them for you. Let's see if you and I are going to give the same kind of answers. The first highlight is here. Perfect. So the first highlight over here talks about the blackboard, the chalk which is present in front of the blackboard, as well as the duster which is used to erase the blackboard. The next highlight, let's have a look. Wonderful. The next highlight is towards the left over there, where we are going to talk about the window. So that is the second object that we were talking about. Let's go for the third highlight. Let's have a look. Wonderful. So the third highlight constitutes of the books and the bag which have been kept onto the desk over there. And finally, the fourth and the final highlight is there over here. Wonderful. So here again we have the desk, and accompanying to that we have the chair. Now it may surprise you all to know that all of these objects can be broadly classified into a single definition. And I guess if you all are smart enough, you all must have already understood. In this particular case, the blackboard, the chalk, the duster, the window, the books, the bag, the desk and the chair, all of them are classified as the term matter. And that's exactly what our scientists have done as well. So scientists have termed all of these substances that you and I see around us as matter. So we now need to understand what is the definition of the term matter. Let's have a look. As far as matter is considered, understand that matter is anything that occupies space and has a mass. It is something that can be easily perceived by our senses. Let's write it down. Anything that has mass and occupies space is called as matter. It is something that which you can perceive through your senses. That, my dear child, is the definition of the term matter. Okay. Now matter over here is fundamentally classified into a total of three types. They are there over here. Let's have a look. The first one is an element, the second one is a compound, and the third one is a mixture. Let's put it up over here. As I said, the first one is an element, the second one is a compound, and the third one is the mixture. Let's understand what these substances exactly are. How are they exactly different from one another? The first substance that we are going to actually have a look at is the substance to the right, which is the mixture. Whenever we talk about a mixture, understand that the elements, the compounds which make up a particular mixture, the constituents that make up a particular mixture can be present in any desired proportion. What do I mean by that? Mixture is like our food items that we consume. They contain everything in a desired proportion. That is, they contain everything in the proportion that you want them to be in. What does that mean? It basically means that when you talk about a mixture, we can add or remove substances according to our need. So that's what you understand by the term mixture. And the basic example of a mixture is the kind of food substances that we eat in day-to-day life. The next definition, the next substance that we are going to understand is obviously going to be a compound. A perfect example of a compound is the molecule of water, which is given by the formula H2O. But the components in a compound are present in a fixed proportion. What does that mean? Compounds, on the other hand, apart from mixtures, are those which have substances in a fixed proportion. So if you change the proportion of the substances, it will affect the compound and it will render it completely different. Now what do I mean by that? Right now, as an example for a compound, you all are seeing water. What is the formula? H2O. It has to have a fixed proportion. You really can't change it. If I attempt to change it, and if I say I want to remove one atom of hydrogen, let's try to remove it. Wonderful. In that particular case, you initially had water, which was given by the formula H2O. Do you think we now have water anymore left after one of the hydrogen atoms was taken away? Absolutely not. So this particular substance ceases to be water. It is not water anymore. In fact, this H and O is now a new radical called as a hydroxyl radical. Finally, the only substance which is left over here is going to be the term element. An element, as we know, it cannot be divided into simpler substances. An element is an absolutely pure substance made up of only one kind of atoms. It cannot be subdivided into two or more simpler substances. So for example, I have a bar of gold over there. It is given by the formula Au. It is made up of gold atoms. It cannot be divided into simpler substances because gold is an element. It's already one of the simplest substances possible. Okay, that being said, the smallest unit of a human body is obviously cells. It's something that we're aware about. What are they responsible for? They are responsible for all the different functions of the body. Now, why am I taking you all to biology over here? Because I am going to have an analogous relationship with chemistry as well. So over here, when we talk about the human body, it is made up of cells. What kind of cells? Fat cells, muscle cells, nerve cells, brain cells, and red blood cells. These are the fundamental units of your body. They build up your body. That is what your body is ultimately made up of. In a similar manner, when we talk in chemistry terms, matter is composed of molecules and molecules are made up of atoms. So I repeat that for you. All of the matter that you see around you is made up of molecules. And if you take that molecule, break it down into the smallest particle possible, you will be getting an atom. Okay. So let's have an experiment to understand exactly the same thing. I have a desk over here, and onto the surface of the desk, I'm going to place a piece of chalk. I want to understand what is the smallest particle possible in a chalk. So what do? I cut it. Cutting once wouldn't be enough. So I'm going to cut it as many number of times as possible. Now in this particular case, when I cut it millions and millions and millions of times, I will understand that chalk is actually made up of atoms. And atoms over here, one must understand, are the building blocks of chemistry. They are the building blocks of matter. So there we have it. This smallest and complete unit of matter is called as an atom. It is the fundamental unit of matter. It is the smallest unit of matter. It is small, but yet it is complete. In a similar manner, all the matter is made up of small particles. And what are these small particles? These particles have only two names. First one is atom and second one is molecule. Let's continue. Now here we have something which we call as the historical background of discovering atoms. Who are the scientists who have helped us out? Let's have a look. The first scientist is an Indian philosopher by the name of Maharishi Kannad. He said that matter is made up of small particles, and the small particles that matter is made up of are called as Parmanu. In a similar manner, we have Democritus, who said that matter, yes, it is made up of particles, and what Maharishi Kannad called as Parmanu, Democritus called them as atoms. The third scientist, very, very famous, John Dalton, built up on the work of Democritus and set up the atomic theory. So Sir John Dalton, building up on what Democritus said, set up something which is called as an atomic theory, where he said that atoms are the smallest indivisible particles of an element and they are the building blocks of matter. Who do we have next? We have J.J. Thomson, who said that there are negatively charged particles present within an atom, and those negatively charged particles present within an atom are obviously called as electrons. Then we have the scientist Rutherford. Rutherford has said that right into the center of the atom, we are going to have something that we call as the nucleus. After that, we have Niels Bohr, who suggested the distribution of electrons which are present in the shells around the nucleus. And finally, we have an atom over here by the name of James Chadwick, who discovered the subatomic particle called as neutron. And after all of these discoveries were made, the atom looks somewhat like this. Protons and neutrons present in the nucleus, electrons present around the nucleus in the form of shells. Okay, have a look. On burning charcoal, it leaves ash at the end. Now, there is one fundamental thing that we must understand over here. Where does the matter of the charcoal go? Think about it. I'll give you an answer. Charcoal is actually a form of carbon. Carbon is an element. Carbon is an element which is given by the formula C. But charcoal is combustible. It can burn. It can catch fire. And whenever the carbon within charcoal burns, it reacts with the oxygen which is present in air and converts to carbon dioxide. Now, carbon dioxide is a colorless gas. So, when charcoal burns, it gives off carbon dioxide, and carbon dioxide gas is liberated, and it is not necessarily a gas that you and I can see. But that does not mean that the matter of the charcoal has vanished away. Never. Charcoal has just converted into a form which you and I can't really see. So, charcoal given by the element carbon, represented by the symbol C, reacts with the oxygen which is present in the atmosphere and converts to carbon dioxide, which is a colorless gas that is liberated. So, has the matter gone anywhere? Not at all. The matter has stayed. The matter has conserved, and that will bring us to the next part that we are soon going to discuss, which is called as the law of conservation of mass, the law of conservation of matter. So, let's have a look over here. There we have it. Left hand side, the charcoal is burning, and the ash is left behind after the charcoal has completely burnt itself. So, these are the scientists which have helped us out throughout this particular great journey. An honorable mention to them. And over here, we are going to discuss the first scientist in detail by the name of Antony Lavoisier. What has happened in his case? He gave us the law of conservation of matter that I was just talking about. What does the law state? In a chemical reaction, the total weight of the reactants is equal to the total weight of the products formed during a chemical reaction. So, whenever a chemical reaction takes place, there are two kinds of substances: reactants towards the left hand side of the arrow, products towards the right hand side of the arrow. And if the law of conservation of matter is valid, the total mass of the reactants is exactly equal to the total mass of the products, provided the masses were measured under exactly the same physical conditions of temperature and pressure. So, for example, we have an equation over here. Hydrogen, combustible substance, can burn, can catch fire. When it burns in an atmosphere of oxygen. Oxygen is a supporter of combustion. So, out of hydrogen and oxygen, who is going to burn? Hydrogen. Who is going to help it in burning? Oxygen. And when hydrogen burns in atmosphere of oxygen, it gives me water. Two reactants, single product. How is the law of conservation of matter valid over here? Let's have a look. The weight of hydrogen, if added to the weight of oxygen, will give me the total mass of the reactants. That should be exactly equal to the weight of water, which is the total mass of products. So, over here, we have the law of conservation of matter that we are going to discuss right now. And obviously, we are going to make it super interesting for you all by coming into the chemical laboratory. Who do we have to help over here? Let's have a look. To the left over there, we have calcium chloride particles. It's a white colored solid. But for this experiment, I require a calcium chloride solution. So, I have taken a test tube which contains water, and within that I have dissolved calcium chloride to convert it to calcium chloride solution. That, my dear child, is my first reactant. Who do we have next? We have sodium sulfate, again a white colored powder. But for the reaction, I require a sodium sulfate solution. So, I have taken a conical flask. What will I add into it? I will be adding the sodium sulfate to it, and to convert it to a solution, I am going to add distilled water. In that case, I will be getting a sodium sulfate solution, which is my second reactant. Now, what should I do? I will be taking all of the reactants together within the conical flask over here. I have a sodium sulfate solution which is present in the conical flask, and I have a calcium chloride solution which is present within the test tube which has been suspended within the conical flask. If I take all of this together and I try to measure the mass, I get an approximate mass of 300.23 grams. Mind you, this is before the chemical reaction has taken place. This is the total mass of the reactants. Now what should I do? I need to initiate the experiment. I need to start the experiment. So what am I going to do? Get rid of the imbalance for some time, and to initiate the experiment, to start the experiment, I want the two solutions to come in contact. So I go left and right, left and right, left and right. And when that happens, I get the products. Who's the first one? Sodium chloride. Who's the second one? Calcium sulfate. And that is the total mass of the products that I need to find out. So let's have a look. Over here, the reaction is going to be like this. Calcium chloride, given by the formula CaCl2, reacts with sodium sulfate by the formula Na2SO4. It gives me calcium sulfate, CaSO4, which is a white colored precipitate indicated by the downward arrow, and sodium chloride, which is nothing but NaCl. To balance, I have a 2 of NaCl. Now this over here are my reactants. This over here are my products. For the law of conservation of matter to be valid, the total mass of reactants have to be equal to the total mass of products. Don't we already have the total mass of reactants? Yes, the total mass of reactants is going to be 300.23 grams. That's something we've already done. So after the products are formed, I'll again place them onto the bean balance and again get exactly the same figure. In this particular case, the calcium sulfate and the sodium chloride formed after the reaction took place, the total mass of the products is exactly coming as 300.23 grams. And that's exactly what I wanted any which way. So in this particular case, I can say that the law of conservation of mass is definitely valid. This verifies, my dear child, the law of conservation of matter.